Section 8.4, this section's on our proportionality theorems. Our objective is going to be we'll know and use the triangle proportionality theorem and its converse, and then use some other proportionality theorems. But before we get into that, we need to have a little discussion on what we mean by proportionality or proportion. Okay, a proportion. Okay, a proportion is an equation where two ratios are equal. So a proportion is an equation, so it's an equal sign. It's got an equal sign, where two ratios, and again, ratio is just a division, which we write division as fractions, saying that two ratios, let's say A divided by B, C divided by D. Okay, so our whole process in solving problems and doing stuff today is going to be first to set up the proportion and then usually to try to solve it. And to solve it, again, we use our means extremes. Our extremes would be the A and the D. Again, remember, the first and the last. There we call the extremes. And then here we have the means, the middle ones. And we know when we multiply the extremes, A times D, okay, it's going to equal the product of the means, B times C. Okay, so we're going to be using that a lot today. Again, remember that's called the means extremes theorem. Okay, so we're going to be using that quite a bit. Okay, so our triangle proportionality theorem, basically what it says is if I have a line parallel to one side of a triangle. Okay, so here we have some parallelness. We have this TU, oops, sorry, too high. We have this TU is parallel to QS. Okay, so there's my line parallel to a side of a triangle. And if that line intersects the other two sides, so it might not intersect, you could have the line out here, and then you couldn't use this theorem, okay? But if that line intersects the two other sides of the triangle, then it divides those two sides proportionally, okay? Meaning the ratio of these two sides, okay, the RT over TQ, is going to equal the ratio of the other two pieces, the RU and the US. Okay, and it's just make sure when you set up this proportion that you don't flip-flop them, because it's always here, the piece to the right over the left, piece to the right over the left, okay? If you do the piece to the left first, you could set this one up the other way around. You could go TQ over RT, T to Q over R to T, but then you would need to set the other one up the other way. You'd have to go U to S over RU. So if you flip the one, you have to flip the other. You just have to make sure you're consistent. Okay. Hey, this works the other way around. If you remember the converse does what? It flips the hypothesis and conclusion. It flips the hypothesis and conclusion. So here, the hypothesis was we had a parallel line. So here's my hypothesis of the original. Hypothesis is TU's parallel to QS. The conclusion then would be I can set up that ratio. What the converse does is it says if a line divides two sides of a triangle proportionally, meaning if these ratios are equal, then that line is parallel. Okay? It just depends what you know first. The triangle proportionality theorem starts with knowing parallel, then knowing the ratios are equal. The converse is if the ratios are equal, then the lines are parallel. It just flips the hypothesis and conclusion. Okay, so here, extra example 1. In the diagram, we know WZ is parallel to XY. So we start out knowing that these two pieces are parallel. This piece, parallel to this one. So we start knowing parallelness, which would be the triangle proportionality theorem. They tell us WX, W to X is 12, V to Z is 10, and Z to, oh, there's a missing Y down here. Z to Y is 8. What is the length of V to W? So we're missing this piece right here. So this is our missing piece. We can use a variable for that. I'm not going to use X because I already have an X. I'm not going to use Y. I'm going to use lowercase, I don't know, maybe an A for that variable. We're trying to find that piece. But since these two are parallel, we know if a line parallel to one side of a triangle, so here we have a line parallel to this side, then it divides these proportionally. So if I put these two sides at a ratio, if we go A over 12, again, that all comes from this side, where that guy comes from. And we went to the left of the parallel line and then to the right. Okay, then I can set up, so then the A, this one would be 10 over 8. Again, that comes from this side. So since these are parallel, there's where that 10 over 8 came from. And so make sure we went to the left of the parallel line, over to the right. Here we went to the left, over the right, to make sure consistent. A over 12, 10 over 8, we know these are going to be equal. So now I just use means extremes. Multiply the extremes, the 8 and the A, 8 times A, and that has to equal to the product of the means. 12 times 10, which is 120. The 12 times the 10, the extreme, the means. Now I need to divide both sides by 8. A then would equal 120 divided by 8, I don't know that one, 15. So V, the length of VW, is 15. Okay. All right, next, here's another one. On the shoe rack shown, B to A is 33. So I'm going to draw this picture again, bigger. The side here, here's C, here's A, here's E, and then we have this guy that comes through the middle that goes B to D. B to A is 33, C to B is 27, C to D is 44, and D to E is 25. Explain why the shelf is not parallel to the floor. Okay, so if this line was parallel to this one, then that means these two sides would have to be in proportion. So let's go ahead and let's set up that proportion. So we would set up this side, the 27 over the 33. Okay, again, we went above that line and then below it, so we have to go above then below. So 44 over 25. So let's simplify these two ratios. So to do that, I'm just going to go 27 over 33 in my calculator, math, enter, enter. It is a fraction. This is 9 over 11. Whereas 44 over 25, I can tell that's automatically bigger than 1. And so simplifying to 44 over 25. These two fractions are obviously not equal, so we'll put not equal. Okay, because they're side lengths. So explain why the shelf is not parallel to the floor. The pieces of each side are not proportional. Okay, another way of saying that, their ratios are not equal. The pieces of each side are not proportional, so these two pieces are not proportional with those two pieces. Okay. All right, another theorem for today. We'll have one more, I believe, after this. Okay, the three parallel lines theorem. Okay, if three parallel lines, so all three of these lines are parallel. This is parallel to that, is parallel to that. So we have three parallel lines. They divide these transversals proportionally. So if I have three parallel lines, so basically if we know that UV is parallel to WX, which is also parallel to YZ, so all three parallel, then we know, so there's our hypothesis, then we know that these sides are proportional, meaning the two pieces of this, UW to WY, is in proportion to the two pieces of this, VX to XZ. And again, remember, make sure you don't flip-flop those sides, UW to WY, VX to XZ. So first piece, second piece, first piece, second piece. Okay. Okay, so we know that that will be proportional if we have three parallel lines. Okay, so in the diagram, we have angle ADE, angle BEF, and angle CFG are all congruent. So all these little angles in here, this little angle, this one, and this one are all congruent, which if we look at these three lines, this transversal, ignoring this one down here, these are all corresponding angles. They're both below the transversal to the right of the parallel line, so we have corresponding angles. Here we have corresponding angles that are congruent. We have corresponding angles are congruent. Since corresponding angles are congruent, we know that those three lines are parallel. So corresponding angles are congruent, so we know that line DA is parallel to line EB, which is parallel to line FC. But it's actually the corresponding angles congruent converse. Okay, so I know these three lines are all parallel. Well, since these three lines are all parallel, they divide these two proportionally. And we're trying to find the distance from D to F. We're looking for that whole distance. But I know these two pieces are going to be proportional. I know D to E to F is going to be equal. So we want D to E to F is going to be equal to A to B, B to C. Okay. When we know D to E is 35, we don't know what E to F is, but we know A to B is 30, and B to C is 12. So now if we use means extremes, take the 35 times the 12, which I don't know that one. 35 times 12 is 420, so there's my extremes. Now multiply the means, E to F times 30, well that's just 30 times EF. Okay, so now to solve that I have to divide both sides by 30. So 420 divided by 30 is 14. So we know E to F is 14. So we know this little distance in here is 14, okay, because we have those three parallel lines. They want us to find D to F. That's that whole thing. So the whole thing, D to F, is going to be equal to DE plus EF. DE is 35 plus EF is 14. 35 plus 14, 30, 49. D to F is 49. Okay. All right, next. The triangle angle bisector theorem. Okay, word of caution. I do this one slightly different. I set up my ratio slightly different than the book does. Okay, just to make you aware of that. I prefer you do it my way, but if you'd like to do it the book way tends to be a little more confusing, so I won't show it that way. So first thing I want you to do is go ahead and cross this guy out right here. Cross that out. Okay. All right, so if a ray bisects an angle, that's divided into two equal pieces, right? Bisect is we have those two equal pieces. Okay. So here I have this ray, and it bisects this angle. We've got the two equal pieces marked there. Then it divides the opposite side into segments whose lengths are proportional to the lengths of the other two sides, meaning the ratio of this piece and this side is going to be equal to the ratio of this piece and this side. So the ratio of, so if this ray, if ray CD, okay, is the angle bisector of angle ACB, then A to D over A to C, again from the same point, we go A to D over A to C, will be the same as B to D over B to C. B to D over B to C. So it's the piece and its side right next to that piece of that opposite side, and this piece and this side are proportional. The book sets up their proportion a little differently. They use this piece and this piece over this piece. It gets confusing, and those ratios tend to get flip-flopped, and so you tend to do them wrong. If you do it this way, if you notice point A is in both of them. It's AD, AC, and then point B is in both of them here, BD, BC. Okay, it'll help you set up those proportions. Okay, so in the diagram, angle BAC is congruent to CAD. So we have an angle bisector here. So we want to find the length from C to D. So I set up my proportion. I'm going to set up this side proportional to that one. Okay, and this should be a point A out here, I believe. Okay, so I know the ratio of B to C to B to A, BC, BA, is going to equal DC, DA. Okay, DC, DA, okay, DC to DA. Okay, so now we plug in. BC is 18, B to A is 42, D to C is Y, D to A is 63. Now we use means extremes. Extremes, 18 times 63, we get 1,134 will equal the means, 42 times y. Okay. Now divide both sides by the 42. Y is equal to 27. So the length of CD is 27. Okay. All right, there's going to be one more video following this. We have a construction we need to do. And there should be plenty of room to do the construction on the way back of your notes. This whole back page is open, so I'm going to do that in a separate short video. Okay, so don't forget to do the construction before you start the practice.